Today I'll be talking about preventing rape in the military through effective DNA computing. Military rape is a problem in the United States and the UK, the rest of the world. The Secretary of Defense, Chuck Hagel, wrote in a memo last summer that preventing the crime of sexual assault remains our main focus, and there are initiatives to prevent sexual assault in the US and in other countries within the military. So a question arises, can we use DNA? Can a DNA database be a deterrent? If a potential perpetrator or serial rapist in the military knows that they will be caught through DNA evidence, is that something that might work? So in an ideal world, imagine, looking at the bottom right of the slide, that all military personnel have a cheek swab taken, and their genetic types or genotypes are uploaded to a reference genotype database. Databases like this already exist in the US for other purposes, like identifying the remains of soldiers. Now in the bottom left, imagine that every rape kit was worked up and that the genotype from a rape kit was uploaded to a genotype evidence database. And then you had both evidence and reference, and then these could be matched automatically by computer. That would be a way that you could implement this database as a deterrent. Unfortunately, DNA mixture evidence is what you find in sexual assault rape kits. There are at least two people who are present, a victim, a perpetrator, and there could be multiple people. DNA mixtures from rapes have 2, 3, 4 people in them. And so the data is not simply 1 or 2 peaks representing the 1 or 2 alleles from an individual's DNA genotype. Instead, as you see in this data taken from a sexual assault case, there are 2 tall peaks, a 7 and a 14, that came from the victim. There are 2 low peaks, a 10 and a 12, that came from an assailant. And this concept of a pattern of data with high peaks and low peaks from 2 or more individuals now requires interpretation. The issue is that current crime labs rely on a human review based on thresholds. They simply look at the surface features of the data and they simplify the data to make it easier for them to interpret. They draw a line at a certain height. The height of the peaks represents the quantity of DNA. Above that line, ignoring peak height, they'll say the DNA is present. Below that height, they say that the alleles are not present. And the result is, depending on where you draw the line, you can have too many possibilities, say 10 possibilities out of the 100 that you started with, or as you see here, the threshold can eliminate the culprit completely. The 10-12 is now gone. Because of this problem, most mixture data in the world is never used for criminal justice. The labs get to the data, they stop, it's thrown out or not reported. And this problem extends to mixture databases. While it's certainly possible to, on the right side of the picture, to build a reference database of all military personnel, making that comparison using alleles, just the lists of peaks, is not workable in databases such as CODIS, which is the FBI's database, because you're not working with genetic types. You're working with lists of alleles, and there's a problem of false hits. And since you can get false identifications extending down to the bottom left, the solution for this with these older allele databases from the 20th century is that the rape kit evidence is not used. It's not uploaded. About 80% of mixture evidence is never uploaded to these types of databases, and so they can't be used to find criminals. A solution is a technology, and this is cybergenetics TrueAllele Technology, which has been around for 15 years. After 10 years of R&D and building statistical models, it became available for use in criminal justice. The way it works is that on the left you see what the user sees, which is a visual interface for entering data, and asking questions of the computer. In the center, the questions go up to a database server, and on the right, that computer represents what in our office is 100 computer processors, each working on a separate problem. For sexual assault cases, they take a few hours per question. So in parallel, you can solve these mixture cases for an entire state or country fairly quickly. The results are then written back to the server in the center, and then a human analyst can look at the objective computer results on their screen shown on the left. What TrueAllele does is, instead of looking at surface features of just whether peaks might be present or absent, it separates the genetic components into different contributors. There could be 2, as shown here, 3, 4, 5, and so it works on the genotypes of each contributor separately, and it solves it using Bayesian computing, where it uses all the data for computer analysis. It doesn't say peaks are too high or too low. It uses the entire pattern. And its goal is to explain the peak pattern. So here's one explanation that's a good explanation. We see 2 tall blue bars. Those are the pair of alleles, the genetic type from the victim, a 7 and a 14. And then in green, in the center, there's DNA present from another person, and that allele pair is represented as a proposal by the computer of 2 green bars, the allele pair 10 and 12. And you can see that the pattern of the heights of those bars, the 2 tall blue bars and the 2 shorter green bars, are at the same height as the data peaks. So what TrueAllele does is it explains the data pattern. It tries out tens or hundreds of thousands of different patterns, moving these bars and peaks all around, never changing the data peaks. It uses the data, and the result is, by having considered tens of thousands of different possibilities, some of which that explain the data very well. You see on the right, the 10-12 is assigned a 90% probability, and others that explain the data partially, and most of the 100 possible allele pairs don't explain the data at all. They get almost 0 probability. What TrueAllele does is it uses the mixture data to concentrate probability for the genotypes of each contributor to where the data is saying the genotypes really have support. And so the output is, instead of throwing out the evidence, instead uncertainty is dealt with probability, which is the standard way of dealing with uncertainty for the last century in science. TrueAllele is used to solve rape cases. This is a case, this article came out this month. A Pittsburgh man was sentenced to 75 to 150 years for rape. Ralph Skundrich was found guilty of 5 counts of involuntary deviant sexual intercourse, as well as multiple counts of sexual assault, indecent assault, terroristic threats, simple assault, and false imprisonment. At the trial in January, I testified to the TrueAllele computer's match statistic on clothing evidence items, where the statistics were all over a quadrillion. This was very easy for the computer. The laboratory's statistic on the same evidence items was under 1 million on each one, and if you divide a quadrillion by 1 million, that's 1 billion, and you see how in criminal trials there's a billion-fold loss on average of identification information, as exemplified in this case. When the information's less, the result can just be inconclusive and the evidence is never used. TrueAllele has been used in criminal trials. There have been about 200 case reports filed on DNA evidence in the United States, in federal court, state court, in court martials, as well as international courts in the UK as well as in Commonwealth countries. And the crimes tend to be fairly serious: armed robbery, child abduction, child molestation. Most of the crimes are murders and rapes, as well as terrorism cases and weapons charges. TrueAllele is a highly validated system. There have been over 20 validation studies, most done with laboratories that are crime labs that are bringing the system on board, including the 3 laboratories two in the US that are now using TrueAllele in daily operation. The reliability measures the sensitivity, specificity, and reproducibility of the results. Sensitivity means the computer is finding that the right person is in there when they're in there. Specificity means it's not finding the wrong person. It's not getting a false hit. And reproducibility means that when the statistical program solves this web of probability equations, that it gets pretty much the same answer every time. So let me show you something from the most recent validation study that was published last month in PLOS ONE, which is an open access scientific peer-reviewed journal. And this was done in collaboration with Virginia. As the title says, TrueAllele Casework on Virginia DNA Mixture Evidence. And it's a comparison of computer and manual interpretation in 72 reported cases that enter the criminal justice system, a dozen of which went to court, most of which resulted in guilty pleas. So the number of zeros, or the logarithm of the match statistic, is a standard measure of information. So a match statistic of a million is a 1 followed by 6 zeros. So 6 is the amount of information. Of a 10 that you see on the x-axis here is a 1 followed by 10 zeros, or 10 billion. And that extends all the way up to about 24 on the right, which is a 1 followed by 24 zeros, or a trillion. This was the range of information found on over 100 matches from evidence items in this study in reported cases. You see that it spans the entire range, which is what you'd expect from random evidence, largely from 3-person mixtures, including sexual assaults. The average match statistic had 11 zeros in it after the 1, which is on the order of 100 billion. So that's what the computer is producing in an automated process. In red, underneath, by comparison, this is what people produced using their current threshold protocols on about half of these mixture items on exactly the same evidence. And you see a red shift all the way to the left of the information distribution moving from 100 billion down to 2 zeros as the average, or about 100. So that's, again, a billion-fold loss in identification information on the same evidence, on the same mixture evidence, when a person can even say anything at all and not say that it's inconclusive. What you're seeing on the bottom is the state-of-the-art of what crime labs do with DNA mixture data. And blue above is the alternative of what computers are now doing with the same evidence. What this does is it enables a mixture database, because what now happens is that mixtures, shown on the bottom left from rape kits, can be separated by a computer into their genotypes and uploaded as probability distributions to, on the top left, a genotype evidence database. Now comparisons can be made, which couldn't have been made before, because of the high specificity of the TrueAllele system. It doesn't have false positives. There's no risk that when you upload evidence, you'll hit 1,000 people on a database, which is what CODIS would do, which is why they restrict the uploads on the current DNA allele-based databases. So that comparison can be made to genotype databases, and then comparisons can be made between rape kits and military personnel through their genetic types. We used this architecture 5 years ago when we reanalyzed all the DNA data from the World Trade Center attack. There were 2,700 victims, and there were over 18,000 victim remains that were highly degraded, charred DNA samples. The way the database architecture worked on the World Trade Center TrueAllele database is, on the left I'm showing the victim remains, and from the missing people, on the top there were personal effects, toothbrushes, hairbrushes, sweaters, from which mixture evidence was often derived. And on the bottom there were family members, and genotypes can be reconstructed from family members as well. So these genotypes were reconstructed from the missing people and the victim remains uploaded to a TrueAllele database and then compared automatically in order to make DNA matches. So this is the proposal of how one could go about using the latest DNA interpretation technology to prevent rape in the military. The first step is to collect DNA from all military personnel. As I said, this has already been done in the U.S. military for other purposes, and it involves using the same database they have, or taking a cheek swab from everyone in the armed forces and uploading that to a genotype database. That part isn't hard. That's been done with databases in the United Kingdom, for example, with the UK, the NDNAD, the National DNA Database, which actually Cybernetics and an earlier TrueAllele product helped in the automated interpretation and uploading of millions of profiles to the National Database in England. The second step is to collect DNA from all rapes. And this is the subtle part. If you read about this issue, you know that victims don't want to come forward because they don't want to speak against a superior officer. And that's been a major problem. The idea here is to let the DNA speak for them. Imagine that there was a requirement that because of better technology, rape crimes must be reported and rape kits must be collected, but the victims did not need to name their accuser for fear of reprisal. So rape kits are known how to be collected, and laboratories can rapidly process rape kits. There's no need for backlogs with rape kits. Every part of generating data is automated. From the amplification step, the readout step, it's mainly done by robots. And so then data, typically mixture data, would be generated. The new part is to get an accurate interpretation of the DNA mixture evidence from these rape kits. And that's where cybernetics and TrueAllele gets involved. Instead of throwing out information or underreporting it, instead, the uncertainty in mixture data can be represented with probability, and these genotype probabilities that are found for every location that are tested in STR kits for each of the unknown contributors can then be inferred automatically by computer from the evidence. Then these genotypes can be uploaded to a genotype database, not to the old style list of alleles, but to a 21st century database that represents information as genotypes that includes probability and knows how to work with it. Now that the evidence can be processed, obtained, turned into data, interpreted and uploaded to a database, now there's the possibility of finding a match between that evidence genotype database and a reference genotype database comprised of military personnel. Again, that's a specific match, and that false positives are not expected to be found based on the extensive validation that's been done on the TrueAllele system. And based on that identification, a rapist can be found by walking from the rape kit evidence up to a genotype database of evidence, matching with a reference genotype database, identifying a rapist, and then ultimately bringing them to justice and prosecuting them. So the proposal is to prevent rape by DNA monitoring, to use TrueAllele computing for genetic surveillance as a deterrence for rape in the military. And a part of the idea behind this comes from work by behavioral economists who look at when do people behave well and when do they behave badly. And in a recent bestseller by Dan Ariely, who studies behavioral economics, the main conclusion from his book is that monitoring people helps prevent people from behaving badly. If you monitor people, then there's a possibility that they will behave better because they know that there are consequences to their actions. For more information about TrueAllele, there's a wealth of information, our publications, courses, newsletters, many presentations, 50 of which are on our TrueAllele YouTube channel. And TrueAllele has been used for all sorts of crimes. If you're going to start reading about it, I suggest you begin with some magazine articles that describe how the system is used in criminal cases, how it's presented in court, and how it's been validated and used to bring people to justice. These slides and this talk should be up on our website in the information section in the next week or so. So if you didn't take very careful notes, not to worry. Thank you very much for coming.